And this is really my pleasure to speak at the analysis seminar and to present my work. It's a joint work with Gilola Stafilani. Okay, so let me start. Oh, what happened? Okay, it works. So let me start with this nonlinear Schrodinger equation. So this is a very famous dispersive model. And then, so the very typical example that we consider for this nonlinear Schrodinger equation is power type nonlinear Schrodinger equation, where we consider this cubic nonlinearity in the equation. And before we move to the hyperbolic setting, that's just stay in the, let's just stay in the Euclidean space for a while. And then we're going to take this initial data to be some HS space, which is like the L2 based Sobolev space. Okay, so that's it. And then we also know that this is a model from physics. So it conserves the mass, which is the L2 norm, and also the energy, which is like a H1 norm plus the potential energy, L4 here. And the mass is at the L2 level, while this energy is at the H1 level. So that is the setup for the equation. And then we would like to ask, are there any global solutions? Because when we have an equation, we would like to solve it. And what I care about is to have a global solution. So here, the answer is yes, of course, you have some global solutions. If you take your initial data in the energy space, say H1, and then you can use the dispersive estimate, which is the so-called Stricher's estimate with a fixed point argument, and then you can obtain some local well-pose theory, and then the length of your time existence will be some delta. Well, this delta is like 1 over H1 norm of this data. Possibly you will have some positive power here, but things I will be hand waving. I will just remove this power because you can see the relation between the size of data and the size of this length of time interval. And since you have the conservation law of H1 means that you can actually iterate, means that you start from the initial time 0, and then you move from 0 to delta, and you start again from delta, then you can go to 2 delta. Okay, so we are happy with this H1 level global well-posedness, but what happens if we slightly lower the regularity of this data? Say we consider a data in H.9 space. Okay, so using the same Stricher's estimate and same fixed point argument, you can always get a fixed point, a local theory, where in this local theory, instead of putting H1 norm, you put this H.9 norm. But unfortunately, you don't have any good properties for this H9 norm, means that you don't have any conserve or upper bound for this norm. Means if you want to iterate in the same way that we iterate in the H1 case, you may have a shrinking step length. Means that it could be possible that you will never go to infinity, you will stop at some finite time. It doesn't mean that we don't have a global solution at, say, H.9 level. It just says that this naive iteration doesn't work very well in this setting. So we want to introduce some different way, or we want to say smart idea. So here comes the Bourgain's high-low method. So what Bourgain did in his paper is that he first considered this Schrodinger equation with some data. Okay, phi is the same data that we considered, but he did a cutoff for the data. He just take the low frequency component of this initial data. And then from Bernstein inequality, you can say that data with this low frequency component will be in H1, and it's relatively large. For example, here you can think of this n to be super large number, but a fixed. Okay, then we're happy because using the iteration or the theory that I just explained to you in the previous slides, you know at least you can solve for this user or for this system, at least for a local time, but actually you can get a global solution. Okay, then this is just one half of this problem, because you still need to consider the difference equation, right? Where this full solution U can be split into a solution U0 where we solve on the left-hand side, and here we solve this difference equation. Okay, so the difference equation has this difference in the nonlinear terms where you have this U cube and the U0 cube. And then let me just cheat a little bit because you know the Schrodinger equation is actually it's the complex function, but that just pretend everything is real for now. Means we have V cube term, V square U0, and V U cube term, something like that. And here the initial data is the high frequency component, right? Okay, so what happened with this half? We really need to have a good understanding of this function V to be able to iterate. So first, we write, this equation into this integral equation, where you use this Duhamel formula, say the solution is the sum of a linear term plus a Duhamel piece. To make my notation more compact, I'm going to denote this Duhamel piece by W. Okay, what was the key ingredient in Bergen's paper? It is the following. You want to show that this Duhamel piece is smooth, means it's in H1 in the energy space, and it's very small in the energy space. So with this ingredient, key ingredient, he was able to run the high-low iteration. I'm going to show you the scheme of this high-low iteration. So first, as I explained, you would like to start at time 0 with the initial data, and then you split your initial data into two halves, a low frequency half and a high frequency half. So you want to run or want to flow to evolve this low frequency data using your nonlinear flow, and then you know your solution will be global and it's in energy, but it's relatively large. And for this high frequency part, you can use this difference equation. This is not derivative Schrodinger equation, this means difference equation. And then you can say, okay, so I have a linear solution. Well, it's linear, it's explicit, but it's kind of rough. And you have this Duhamel piece. This is very nice because it's very small in the energy space. So that's what happens in the first iteration. So you can go from time 0 to delta 1. And then you recognize that, okay, so I have two pieces who are very nice. One is this energy solution in U0, and you also have another small part in the energy space, which is this Duhamel term. Okay, and then the size of this U0 will be very large, that n to the 1 minus 1. And this Duhamel piece will be very, very small, like n to the some negative power. And then you sort of combine, you merge these two terms into a new initial data, which is what I call U1 here. And then you can tell that since this term will contribute a little bit, so the energy or the H1 norm of this U1 will be almost dominated by this term. Okay. Then you want to evolve this new initial data using your nonlinear flow, and then you get a global solution. At least you can have some local solution. Then what happens with this rough linear part? So for this rough linear part, you want to evolve it again using the difference equation. And then you will see a small Duhamel piece in the energy space again, plus a rough linear solution. Okay, so my one remark here is that in the second iteration, actually the step length is not shrinking. The reason why I claim this is not shrinking is that since you only absorb a little bit, which is W0 here into your initial data, and then the step length will still dominated by this one. So there's no shrinking happens, which is good. And then I guess you know what would happen in the third iteration. So this is the second iteration. So what would happen here is that you combine this U1, a smooth solution, with this small thing that you generate from this difference equation, and then you have a new initial data again, it enters in your next iteration. And then you evolve this using a difference equation, and then to rewrite this into a linear part plus a Duhamel piece. Okay, so that's it. That's how you want to run the iteration. And then you can actually continue this iteration to obtain a global solution. So you globalize your solution using this kind of high-low decomposition. And then if you still remember that I claimed the step length won't be shrinking, and you want to guarantee somehow every time you put or you insert this small piece W1 or W0 into this smoother solution, it won't ruin the structure, it won't ruin the iteration. So this thing will give you some restrictions on the regularity of your initial data. And Bourgain proves that if your solution, if your data is in HS space where S is larger than 3/5, you can actually have global solutions. But there's no scattering argument in Bourgain's paper. So by scattering, I mean a nonlinear solution behaves like a linear solution as t goes to either positive infinity or negative infinity. Okay, and then so by the work, okay, by the work of I-team, I didn't have enough space here, so I wrote the name down there. Coliander Q, Stefanani, Kakota, and Tao. They introduced the I method to lower the index from 3/5 in Bourgain's work to 4/7. And I guess in this work, they used
so
the second
so Xueying, that's also called the I-team.
Yeah, the I-team.
Yeah, so that's the name, I guess, is coined by Tao. Yeah, so maybe you're too young, you don't know their stories. So yeah, Kale is the student of Kleinerman. So Stefanani is a student of Koenig. So they are experts in PDE, but Tao knows nothing from PDE. So I think these two introduce the equation to him, and then they wrote a lot of joint work in the last 10 years.
Yeah.
Okay. Yeah.
Yeah. So okay. So yeah, so this I-team, they introduced this I method to be able to lower the index. And in Coliander, Rory, and Dodson's work, they even lowered the index to 1/3 and 1/4 respectively. Okay, that's the story. Then I guess I still owe you the key ingredient. I didn't tell you why we could show, or Bourgain could show, the smallness of this Duhamel piece in the energy space. So that is what I want to tell you. So the key ingredient here is that you want to show the H1 norm of this Duhamel piece is very, very small. And what Bourgain use is what you can call XSB space or Bourgain space. Each type of space are defined using Fourier transform. Okay, so I don't want to give you the definition, a formal definition of this type of space, but I'm going to tell you that what you can gain after you use this space. So pretend you have two functions or solutions. They are very frequency localized. One is localized low frequency N, the other one is localized frequency high frequency M. And then you want to act some derivative or some gradient on the product of these two functions. In calculus, we would expect that these two functions will somehow take turns to share this gradient. But using this XSB spaces, you can actually ask the low frequency function to carry all the gradients. So this key property or the key estimate will give you the possibility to show this Duhamel piece is very small in the energy space. Okay, then at this moment, you may want to say, okay, so it is possible for us to mimic what Bourgain did in his paper and transfer all his estimate strategy to the hyperbolic spaces. Then my answer, or possibly, I mean, this is no. because we have something wrong in the Fourier transform. And let me just quickly recall what happens in the R2 case. So in R2, you have this very typical Fourier transform where in the orange term here, I put this eigenfunction. And if you want to write the Fourier transform for the hyperbolic space, you have a different version of eigenfunction. I hide the formula for this eigenfunction, but just put this eigenfunction here. And because of the difference, we will see some unfriendly term showing up in the inverse form and the pressure L. Okay, maybe you want to say, okay, so maybe this is just like a different formula. But one bad news, really bad news, is that we don't have the Fourier convolution theorem, which is, I guess, my favorite theorem, because you really need the Fourier convolution theorem to deal with the nonlinear term, especially the second half. Means you want to say the Fourier transform of the product of functions equals the convolution of the Fourier transforms. Since you don't have that, I mean, maybe it's not even possible for us to use this XSB space. Then knowing the bad news, what would be, doing for this project? So we want to know if there's any other way to recover the same estimate without using any Fourier transform. Okay, so let's just recall what this estimate tells us. So this estimate basically tells us you start with something rough, but you end up with something smoother. That's it. And are there any other properties or any other estimate that you can use to recover this idea? So what we thought here is the local smoothing estimate. Okay, so I show you this local smoothing estimate on R2. So by local, I mean you need to put a weight. So either you put a weight or you somehow restrict yourself in a ball. So let's just consider this weighted version. And smoothing means that let's just ignore the weight for a moment. Smoothing means you start with something in L2 and you end up with your linear solution in H1/2. Okay, so you gain regularity. So that might be the hope for us to close this estimate or to recover this estimate. And let me also show you the nonlinear version of this local smoothing estimate. How I'm doing with the time? Can I still have, sorry, I don't hear you.
You have 5 minutes.
Okay, sure.
Yeah.
So I'm going to try to present the calculation of this key estimate in the second half of my slides. Okay, 3-line proof. So first, let me recall what we want to prove. We want to show the H1 norm of this Duhamel piece is very, very small. And this is the formula for this Duhamel piece, correct? I did nothing, just rewrite the definition. And then you can use Schrieffer's estimate to say, you can actually act this derivative on the nonlinear term, all right? And then, since I know this nonlinear term, capital F, it would be the difference of these two things. And I just want to pretend everything is real. And also, I'm going to just show you as an example by taking this V cube term as my capital F. Okay, all the other two terms should be very similar, but let's just focus on this term. And then what's next? I'm going to use a very important theorem in Calculus 1, which is the chain rule. So you would like to rewrite, somehow split the derivative on this nonlinear term into the derivative of V and 2 other copies of V's. And then, so what next? We want to somehow use the local smoothing estimate, right? But you don't see the weight for now, and you don't see the derivative, or you see the derivative is here. Okay, so to be able to use the local smoothing estimate, let me just introduce the weight and split half gradient there. Okay, since you introduce the weight, you need to ask the other 2 V functions to share the positive weight. So that's it. That's the Holder inequality. And next, I can rewrite. So if you look at this V function here, I can rewrite this V using its integral equation by writing it into a linear term plus a Duhamel piece. Okay, so that's nothing, just split this into an integral equation. Then we are ready to use our local smoothing estimate. So the right term here, we use the linear version of local smoothing where you treat whatever I boxed it as the function f here. So you have this exactly identical linear formula here. And then you have this L2 norm of f. And you are happy because this solution, this initial data here has the high frequency component. And then you can use Bernstein again to say this is very small, because you can somehow bounded this by n to the 1/2, which is the regular here minus s. Okay, so this term is very small. And this term, this yellow term is due to the nonlinear version of the local smoothing. So this is what you have there. Okay, so what's next? We still need to understand, or still need to.
Xueying, you are trying to tell us without using Fourier transform, you want to prove
the same estimate.
The same estimate.
Yes.
Okay. For the
R2 case.
Okay.
Yeah, for the R2 case. I'm almost there, trust me. And then so here you would like to deal with this V function with this positive weight. And the only, thing that we can control this, or maybe the only thing I know to control this is the radial Sobolev embedding, because you can absorb this positive weight into some kind of derivatives of it. So here you first take out this integration in time using Holder inequality, and then you say, so this positive weight can be absorbed by this radial Sobolev embedding. And then this is, since V is essentially high frequency, so it's also very small. Okay, so that's the only place where we need this radial assumption on the initial data. And so that's it. And in the very last step here, I want to show you that this term, this nonlinear term, is also very small by using some Holder inequality. So if you just do Holder inequality, and this term will be the same as the orange term, and this, you can think of this as a mass conservation law. And now you are happy because you really have smallness, and then you recover the Bergen's estimate. So that's it. That's the strategy. Okay, so I only have my last slides here. I'm going to show you the result and also tell you like why this strategy would work for a hyperbolic space. So the result here is that you consider this cubic Schrödinger equation on a hyperbolic space with initial data phi in some HS space, and you have this radial assumption. Then you can prove that the solution is global well-posed and it scatters when this S is larger than 3/4. Okay, so the reason why we think this will work is that all the tools that we have solved before are in my list. So we only use Stricher's estimate, local smoothing, and radial Sobolev embedding. Okay, so for Stricher's estimate, it is even better in the hyperbolic space. Okay, so it gave us some positive news that you can recover the estimate. And for the local smoothing, it is identical, actually, identical to the one we used, the one I presented in the previous page. And for the radial Sobolev embedding, it is even better, because if you still remember the weight I put there, it was like a polynomial weight. And in the hyperbolic setting, you can even put exponential weight, means you can absorb more. Okay, so that's another good news. And things here, we have some scattering result, means that we actually combine some Morowitz estimate into our argument when we run this iteration, so we can have some better control. Things that I don't even mention this Morowitz estimate in my talk, so I'm going to skip this. But my point here is that, yes, with same or even better tools that we saw in previous slides, we can close the argument and then we can obtain the global well-posed net scattering for radio initial data in this range. That's it, I guess. That's my end of talk. Thank you.